Welcome, everyone. I'm glad to meet you again in the fourth webinar of this series. The series of the webinars named RSPile Webinar Series, and today is the fourth part and the last part of the series, and it's about structural design and capacity ratio. This is very important feature in RSPile, and please be noted that you can type your questions in the side panel, in the question zone, so that we can answer them at the end of the webinar. And if there will be no enough time for all the questions written, so we will, anyway, we shall answer all the questions and send the list of the questions and answers to everybody. For the new registrants and attendees, we're talking about our company, Rock Science here. Rock Science is a world leader in developing innovative 2D and 3D software for civil, mining, and geotechnical engineers. For over 25 years, we've built geotechnical tools used by over 10,000 users around the world. We are dedicated to delivering industry-leading software programs, exceptional customer service, and unparalleled technical expertise that engineers can rely on. This is our office in Toronto. The building is an iconic building. Tourists come usually and take photos for this one. About this series, we had 3 previous parts that were cast in February 22 and March 30 and April 19, successively. The first one was about the pile capacity. The second one was about the axial and lateral pile analysis. The third one, the previous one, was about the analysis of pile groups. Today we are in the fourth part, structural design and capacity ratio. Today is May 17 to 2023. And this is me. My name is Ahmed Mufty. I hold a PhD in geotechnical engineering, and I'm a professional engineer in Ontario, Canada. And I'm a geomechanics specialist in rock science in the office of Rock Science in Toronto, Canada. Let's start our subjects. So we will see first what RSPile does. What does the software do? The software, as previously mentioned in the previous webinars, it is made of 3 major modes that are the capacity calculations for individual piles, single or multiple piles analysis, and pile groups. And we added a 4th mode, which is for structural design. Today we're talking about this one. Individual piles capacity, as we talked about in the previous webinars. So they consist of driven piles and board piles, and also it has a specific feature for pile capacity table generator. I'll not talk in detail about these because you can refer back to the previous webinars. The single pile analysis may be 1 pile, maybe 100 piles, maybe 1,000 piles. It doesn't matter as long as you are analyzing these piles individually. So you can have all your piles in the project analyzed in the same time. It has the behavior under loads, so any types of loads. The pushover analysis for sensitivity and check what will be the response of the pile for different displacements. I'll shut off my video so that you can see the things better. The single pile analysis also has length analysis. So different lengths gives you different behavior. The behavior under soil displacement, this is usually important in slope stability analysis, and it's integrated with slide 2. And also you can produce TZ and PY curves, and you can produce the pile stiffness for the structural engineer. Analysis of pile groups was the previous webinar, and it's about pile cap design, shape, elevation, and also pile patterns. You can add any patterns you want, orientation, connectivity, group effects. Then the loading, maybe general loading on pile caps. If you are in the single pile mode, now we can apply whether it's a single pile analysis, multiple pile analysis, or group analysis, as long as you can apply reinforced concrete sections, then you can apply structural options of interaction diagrams. For the first time, we're introducing interaction diagrams and capacity ratio for calculation of structural features, structural capacity and features of the reinforced concrete sections. Now, interaction diagrams in RSPile can use different concrete stress-strain relations. So we have the ACI Whitney block and the modified Ognestad method. And we are up to adding more stress-strain relations for the concrete. Also, in the interaction diagrams, we can define different material factors. We can define single factors and ACI factors, and we are intending also to add more factors. Maybe in the future, we can add Euro code. It depends all on the plan we're moving on. It's a very heavy plan, in fact. Then you can see a 3D view for the interaction surface. Meanwhile, you can calculate the capacity ratio if you have factored interaction diagram. So if you have a factored interaction diagram, you can know whether your sections are adequate or not adequate so that you can change the design. And this depends on the biaxial moment capacity and axial load capacity. Returning back to structural features in RSPile, generally, we have 4 section types in the analysis. These section types are elastic sections, elastic plastic sections, reinforced concrete section, and pre-stressed sections. So all these are available in RSPile. Of course, in elastic sections, you don't have failure. In elastic plastic sections, you can apply a limit to the moment capacity of the section. So wherever the section reaches that moment, the program keeps the moment unchanged. You can't, the analysis will not add to that moment. So it can be the plastic moment, and it can be the maximum elastic moment, or any moment you want. The reinforced concrete sections, now we have the interaction diagrams and the capacity ratio. This is how you can measure the section is acceptable or not. We will not say failing, because failing means you exceeded the unfactored interaction diagram. You are outside the unfactored interaction surface. But when you are between the unfactored interaction surface and the factored interaction surface, that's the section is unacceptable code-wise. But even though it may be outside the unfactored surface, for the pre-stressed concrete, the only way for now in RSPile to know that your section is not adequate, that you have a divergence in the solution, your pile will not be adequate to hold the loads you have applied. The cross sections that are used for these 4 types of section types. So in the elastic sections, we may analyze circular solid sections, rectangular sections, pipes, typical rolled sections, steel rolled sections like American standards or European standards. Canadian standards. Typical rolled sections, they have built-in properties in RSPile. You can use them directly. And user-defined sections where you define the modulus of elasticity and the equivalent diameter of these sections, and the program will solve it for you. In the plastic sections, we have three tabs: the circular solid sections, rectangular sections, and the pipes. While in reinforced concrete and pre-stressed concrete, the sections that you can analyze in RSPile are circular sections or rectangular sections. For the plastic moment, in elastic plastic sections, applying a plastic moment, or let's say a maximum allowable moment, you will allow a plastic hinge to exist or occur. You have full plastic moment to be given by the user. So you need to calculate that separately if you want to give a plastic moment. But if you want to give just a limit for the moment, you can use any limit you want. In fact, if you go very plastic, it won't be for practical design, because if you have a plastic hinge, the pile will be in a very high displacement mode. So it's not for practical design, but it's for check whether these sections are okay for you or not. So you can increase the sections until you get a suitable resistance to the moments and the shears and the loads applied. Of course, this needs a high number of iterations. So be sure that if you stop at specific number of iterations, increase your iterations. Divergence usually occurs if the section fails and it can't hold any moment anymore. Sections are limited to pipes and circles and rectangles. This is also one of the limits on this method. The pre-stressed concrete sections allows, of course, pre-stressed concrete section design. So you can design the location of the bars, location of the pre-stressed bars. Iterations are very fast unless there is failure. So when there is divergence, you can see failure in the pile can be detected by the divergence. It's useful for practical design, and it applies only to circular and rectangular sections. In plastic sections, for example, you have an elastic plastic pile section, and you start adding loads on this pile, causing increase in bending moments. And the bending moments and the loads, axial loads and bending moment, will give you some stresses that at the edges of the section, which called the extreme fiber stresses. If these are less than Fy, the yield stress, the yield strength, then the pile or the section is still in the elastic ring. If it increases until it reaches Fy, so this is the maximum elastic condition that we can reach. And if the moments increase more, then you will see that part of the section from the edge started to be plastic, while the core of the pile or the section is still under elastic condition. And when you reach the fully plastic condition, there is no elastic part in that section anymore. And in this case, you will have plastic hinge started to form. The plastic deformations are too high. The elastic plastic deformation, the intermediate one, are high, but less than the plastic deformations. Elastic deformations are the ones we usually target. Let's have a demo on this one. I like to show you a demo on this one. So this is a pipe pile having a diameter, outer diameter of 300 millimeters, and that's the Fy and the modulus, and the thickness is 6 millimeters. Then I'm calculating here the moment of inertia and the elastic moment, then the plastic moment. Of course, it's easy to calculate the plastic moment and the elastic moment is from the Fy, using Fy equals mc over I, if you remember this. And the plastic moment is a block, as we have seen in the previous slide. It's a rectangular block above the neutral axis and rectangular block under the neutral axis. Anyway, for the 6 millimeter pipe, we are getting a plastic moment of 558 kilonewtons meter. So we remember this figure. If we increase the thickness from 6 to 12, this will be double to around 1080 kilonewtons meter. Now with this, I will apply these to this distribution of pipes under, you can see we have 9 pipes, 9 pipe piles. I will not go into the details how we erected this model and like that, because you have seen this in the previous webinar. So we have 9 piles here, which are made of pipes of 300 millimeters, 6 millimeter thickness. And we applied a load, a shear of 5. Let me see the load. So the load is in cap design, and you will find it here in loading. So we applied 6,000 kilonewtons. That means each pile is getting 6,000 over 9. If there is no group effect. If there is group effect, there will be difference, of course. Of course, the group effect here is very, very small because of the high spacing between the installed piles. Pile number 6 is the worst case. So we will, if we graph pile number 6, we will get these results. You can see how the plastic hinge is formed in the displacement, in the deflected shape. And after the plastic hinge, you have, we use the soil as elastic so that we demonstrate this very well. So nothing is resisting this rotation except the springs of the soil. But the pile itself, it's having a plastic hinge here with a moment equal to the plastic moment. And you can feel it here also in the rotation. Rotation jumps from an elastic case to a plastic case, plastic condition. The maximum moment, you can see it here, 570, which is the one, if you remember, I talked about, and I calculated it in the table. So that's the 570, the maximum plastic moment. So what I will do, I will increase the thickness because I'm a designer and I want a better pile. So I increase the thickness to the same situation exactly, 300 millimeters, 9 piles, the same load, only the thickness has increased to 12. I got almost half the displacement, very, very little displacement compared to that one. This is 70. It's still high because the pipe is small. This is made for demonstration so that you can feel the values. The first one was reaching 160 centimeters or something. And when you go to the analysis, you will still find the maximum moment. Here it's around, in the beginning, it's around 700, then goes back again to around 599, 660. Of course, because it is stiffer, it will get more moment now, right? So we're talking about 670, almost the maximum. And you remember the figure in the table was 1080, which means the pile is adequate if compared to plastic moment. Although maybe very close or exceeded a little bit the elastic range. Of course, if you take a higher, a larger thickness, like you go instead of 12 millimeters to 15 millimeters, or you increase the diameter from 300 to 400 or 450, you will get better results. And until you get satisfied with your displacement, and there is no plastic hinge anymore. We need to talk about something important, because when we are going to apply biaxial moment and axial load, etc., we need to know what is the right-hand rule. So the right-hand rule, you can see this is my hand. So the right-hand rule is how your fingers are rotating around the axis. So the thumb is the axis and the rest of the fingers are showing the rotation. That's how we define the positive moments or the positive couples. And you may denote them as an arrow with two heads, or you can use one arrow with a rotating arrow for the moment direction. Anyway, if you say the moment is positive around x-axis, then you know what is that meaning. For the axis orientation, there is also a right-hand rule, which is we are also following. So x, y, and z, when they are in a situation that z is in the direction of the thumb, and you're rotating from x to y, that means, with the fingers, I mean, that means you are following the right-hand rule. Loads on piles. What are the loads on piles that cause combined loading? So combined loading arises from having an axial load and biaxial moment. Or maybe one of the moments is zero. There's no moment around one of the axes. So you will have a moment around the other axes. Then that will be a uniaxial moment. Axial load with uniaxial moment. But the general one is an axial load with biaxial moment. So there will be a point of application for the load that is out of x prime and y prime, which are the local axes of the section. And there will be a location for the neutral axis is not anymore parallel to x prime or y prime. Even the section is symmetrical. So our job is to construct an interaction surface or an interaction diagram. We need to find out where is this neutral axis located, like yn or xn, and in the same time, what is the orientation of this neutral axis beta? So this is what the program does. Of course, we continue assuming that the strains are linear. Plane sections before bending remain plane after bending. We also added in RSPile updating to the bending stiffness in the finite element solution, which is rare usually, but it's more accurate. So we do this in RSPile. So your bending stiffness gets updated every iteration of solution. If you see how this bending stiffness gets affected with the bending moment, of course, the direct relation between the two is that EI equals M over the rotation of the section phi. So it starts with no moment, so only axial load, and starts in can you mute, please, yourself? This starts with an elastic region that is usually nonlinear because of the concrete is nonlinear. If the concrete was a linear material, this would be a straight line. Then turns into a point where cracking of the concrete starts very fast and progressive cracking ends with a plastic hinge formation when the reinforcement yields. And after that, there's no much gain in the bending stiffness, no much loss in the bending stiffness. Then after that, you reach the ultimate capacity, and there will be no much gain in bending moment. This is for a load of axial load of P1, and when you increase the load, you get an axial load like P2 greater than P1, then you will have a different relation between moment and EI. That is what RSPile does for updating. So it calculates the bending stiffness for you in each step of loading. And each section, through the depth of the pile, has a different axial load, right? Because if you put some load at the top of the pile, you will get less loads while going with the depth because of the deduction of the soil resistance. By the way, this is the elastic modulus of concrete multiplied by I gross. This is what is used usually in elastic analysis of reinforced concrete piles. So this is how the M5 curves look like with depth. So they are not anymore the same M5 curves. While most of the programs and most of the people who analyze piles use a single M5 curve for analysis. You can read about this in our article in our website. The article name is Improved Analysis of Reinforced Concrete Piles in RSPile. And that's the link for it. You can find it easily by typing the name. The other feature in RSPile for structural design is the reinforced concrete section detail. So this is a very important feature in RSPile because you can design circular or rectangular or square pile sections as reinforced concrete, giving, of course, the F sub C prime, which is the cylindrical strength of the concrete. How much is the diameter? Then you click on design, and you can have as many sections as you want. You name the section and go in. For example, this is from a real project. The pile may not have the same reinforcement along the depth and may not have also the same section. Maybe the section here is 1 meter, the section below is 0.8 meters. Let's say generally the piles are having the same section along the pile, although we have something called telescopic piles, something we call belt-shaped piles at the base, and these have been discussed in the previous webinars. So here at this section, we have bundles of 2 bars of 32 millimeters, while at this section below this point, we have only 1 bar not bundled anymore. And it's changed from 32 millimeters to 25 millimeters. So you can design your pile defining your section. So you have, this is a section A1, and this is a section A2, and you define your reinforcement within the section designer. See how the section designer look like. You can define the pattern of reinforcement. You may have different patterns of reinforcement. For example, bundle, then triples, then singles, different diameters, so you can apply different patterns. And each pattern may be radial or peripheral if you have a square or rectangular section, and maybe also through all the section. And you can define the cover and the number of bars. And you can see also, it gives you immediately how much is the reinforcement ratio for this pattern, and how much is the reinforcement ratio total for all patterns. So if you have 3-4 patterns, when you move from a pattern to another in the same section, you will find this figure is changing while this figure is constant. Then you apply, of course, the yield strength and the elastic modulus of these bars. So you may have even 2 types of bars. Yes, because you have 2 patterns. You may make a pattern for 500 MPa, another pattern for 400 MPa. You can apply a casing, permanent casing around the pile. You can apply a core, an empty or filled core in the middle here. And you can apply an I-beam in the middle of the section. From a chosen section, all built in. You choose the section from the built-in table. Now, if you have the section A1 and section A2, you can build your pile with defining pile sections through a feature called Pile Type Editor, or this dialog box you can read, Edit Pile Types. It's the Pile Type Editor. You can accomplish your pile by using different sections, and each section has its own length. So you remember the reinforcement length of the first section is 10 meters, for example. The section is 11 meters. So you have different sections for different lengths. And you can define these sections by length or by elevation also. You can see them by elevation, you can see them by the length. You can have orientation for the pile, you can have rotation, inclination, and also you can add a bell, an enlarged base, and you cannot have it. It's up to you. It's up how your pile is. So if you don't have a bell, you will end up with a straight section. If you have a bell, it will be added to the end only. We have gone through these in the previous webinar. So if you want the details, you please refer to the previous webinars. Let's go to the interaction diagram. Let's see what is the situation in a combined loading of a reinforced concrete section. You will find here the gray part is under compression. The pink part, the pink area, is concrete under tension, while the white part is stacked concrete, does not participate to the strength of the section. So if you want to add the tension to your stress-strain curves, you need to use a stress-strain model that has tension. For example, the Whitney block of ACI does not include the tension. So ACI code assumes that the cracked part of the concrete includes the tension part. It does not count for the tension resistance. So you can see different directions for the neutral axis and different locations for the neutral axis, depending on the location of the point of loading. The point of loading is usually taken or recognized by EY, which is the eccentricity from the x-axis, and EX, which is the eccentricity from the y-axis. EX and EY will take the same sign convention of the axes. So EY above the x is positive. EX to the left of y is negative. That's why you need to remember the right-hand rule, how to apply it, because some of the moments you need to apply them negative. So these are different cases. You can have a look to them later in the video that will be cast on YouTube. It's interesting, and also it gives you a lot of ideas how the section will behave under different loading conditions. For example, if you have a concentrated load in the middle, no moments. So where is the neutral axis? The neutral axis is at an infinite distance. So how the program does count for this one, there's of course a method for this. We also limit the maximum distance of the neutral axis to a multiple of the dimension of the section. Also, the same happens here for the tension. So if you have a low tension, the whole section is not cracked, but it is under the tensile strength of the concrete. While if the tension increases, the only thing will take the tension is only the reinforcement, which is not shown here. So the whole concrete will be cracked. This is just how to show you how the concrete behaves in the section under different loading conditions. Look here how I am applying the moments. This is positive moment around X, and this is positive moment around Y. Two double arrows, as we said in the right-hand rule definitions. These are the positive moments. And the definition of the green point is a compression force, red point is a tension force, and blah, blah. The angle to the direction of load application is very important while constructing the interaction diagram. Why it is important? The angle is important because it defines first, it is defined by EY and EX, so that alpha is the angle. So remember, alpha is taken from X prime for the point of loading, not for the moments. And I will tell you why later. So it does not define the tangent of my over mx. It defines the tangent of ey over ex. So ey over ex is the tangent of alpha, not my over mx. Remember that. The importance of this alpha is that if you have a trial for the neutral axis, then you can locate your tension, your tensile force in the section, the tension resultant, and the compression resultant, and your force, the axial load where it is applied. They all lie in the same line. And that these three should be in equilibrium. These two from the internal forces, and this is the external. All these have been taken into consideration, and they are very well formulated in RSPile. Now, for each alpha, for each angle of load application, we have a certain interaction diagram that is between the resultant moment capacity with the resultant axial load capacity. So each point here represents an axial load capacity versus bending moment capacity, but in the direction of alpha. If you have uniaxial bending moment, then alpha is either 0 or 90 degrees. But what happens if I want to see the moment capacity around all alphas, but for a certain load? So I define the interaction diagram for a specific load and for different alphas. So any alpha, you can find how much. See, this axis is m and x. This axis is m and y. N is used for nominal. So it's the maximum capacity, ultimate capacity of the section. So that's why alpha is taken in this diagram, is taken from the m and y axis. If you put this in your in front of you and you put ex, ey in front of you, you will understand why. So remember, when you read the values from our interaction diagrams, your alpha starts from the y-axis counterclockwise in the m and y, m and x diagram, not in anything else. Points that affect you while constructing the interaction diagram. So you go to project settings in RSPile and you will find interaction diagram tab. You press on this one, you will see here that you need to choose what is the stress strain model you're using. We have now only two, which is Whitney block and modified Ognestat. They are two, but they are very important ones. They're very effective, and most of the world use them. Then you have to calculate factored interaction diagrams or not. Do you want the factored or not? If you don't want the factored, then there is no meaning for calculating the capacity ratio. So when you uncheck this one, this is unchecked automatically. But if you check this one, you can ignore the capacity ratio calculations. Anyway, it's better to have them both. Then you apply the factor to the unfactored moments and loads that you constructed the outer shell of the interaction diagram with. So you have single factor, you can apply a single factor. You put your factor, whatever you want. Then there is the standard ACI 318 committees factors, this building code. So we have the number of P divisions. How many P divisions you have, that affects the solution. How many divisions in alpha you will take that affects the solution. And it takes long time, by the way. If you change a little bit higher, it will take longer time. Number of slices in the reinforced concrete section. Of course, we're not analyzing the section theoretically 100%. We are using numerical methods. So there are slicing in the concrete, and the slicing in both directions. So if you move from 100 slices to 200 slices, you're not doubling the time, you're multiplying the time by 4. Time will be affected by all the above, as I said. The stress-strain curve chosen, it affects your results, of course, whether the block or the nonlinear curve, the Whitney block or the Ogdenstadt method. Then number of reinforced concrete sections in the model. If you have one reinforced concrete section, it's less time, of course, than you have if you have like 20, 30 sections. The program analyzes them all and constructs their 3D interaction surface before starting anything else, so it will take some time. We're working on this. Maybe we will have a choice for the user in the next releases. This is how the ACI 318 factors look like. So it depends on the strain. That's why it's not a single factor. It changes with the location of the point in the interaction diagram. Let's go to a demo. Let's see how interaction diagrams are made or constructed. So this is an example. The example consists of tutorial 14 sections, if you have seen our tutorial 14 before. So tutorial 14 shows 2 piles, 30 centimeters and 35 centimeters in dimensions. One is square and one is circular. They are designed in a way they will have almost the similar interaction diagrams. I chose them specifically so that you can compare what happens with the circular ones. So after designing the sections, putting the reinforcement, then we go to project settings, and we go to interaction diagram, and we choose which one we want to use, modified Ogdenstadt or the Whitney block. Then we choose the ACI 318 factors. Then after that, in the project settings also you can see in the advanced, I increased the number of slices to 200. It's just better than 100 sometimes. It depends, of course, on your trials. As much you work on it, you will have more experience what to do. Then you can press compute. After compute, you go to results. Then you press plot interaction diagrams. When you plot interaction diagrams, you will get this layout. Of course, it will, when you press plot, let me show you what happens. It's better. So we are here. I press this one. It gives me, since this is a small dialog box, I choose the sections that I want to draw the interaction diagrams for. I put the alpha angle that I want, and I put the load I want. So for this example, I used 45 degrees for the angle, and I think 4,000 or 6,000, let me see. So you can see them here. Oh, it's not there. It means let's change it. So this is 45 angle, and this one is 6,000, let's say. Then we compute again. Okay. I think I mixed up with the other one. I think it was 600, not 6,000. So you press on compute, and you will get your sections here. Then you can also check the factor, then you will get the factored also. So these are unfactored interaction diagram, and these are factored interaction diagrams. And you can see one of them or both sections. It's up to you which one you choose. Then let's go to the 3D. If you go to the 3D, you will see this one. This is coming for the square. You can see also for the circular. It's very beautiful, right? You can zoom it out zoom it in, and you will see the maximums that you got along all the surface here for the unfactored. If you want the factored, you can have a click here, checkbox, click the checkbox for the factored, and you will see the factored interaction surface inside the outer shell of the unfactored interaction surface. You can have different transparency. So let's say we shall use 80-80 and see what will happen. See, it's beautiful. You can feel everything in it. Okay, so let's continue. So that is how the interaction diagrams are constructed. Now, if your points of loading will fall inside the factored interaction diagram, then the capacity ratio will be less than 1. If it falls outside the factored interaction diagram, the capacity ratio will increase than 1. And if it increases more than 1, the capacity ratio, the tables will show you red cells. Let us see the capacity ratio. How it works, this is how it works. So we have unfactored interaction diagram and we have factored interaction diagram. Of course, the factored is not continued parallel after the cap. There's a cap, which is the maximum compression that the section can hold, factored compression. And this has two values, in fact, one for the spirally tied columns and normal tied columns. So we use the tied columns, not the spiral, because if you use a spiral, you need to have a lot of spiral reinforcement, which is not applicable in piles. It will be very close spacing for large diameter piles, and the concrete will not flow properly. That's why most of the piles have limits for the minimum spacing. It's different than the design of columns. And we have two methods to calculate the capacity ratio, depending on the MU/PU vector. MU/PU are the factored loads that you have that you have got them from the results. So these are considered the factored loads. The vector to the point of the load divided by the vector in the same direction that crosses the factored interaction diagram, that is called the capacity ratio. This is a method one. The second method, I go to the level of the P that I am applying and check only the moment vector. So we have moment here divided by the total moment. Now we have method one applied in RSPile. Method two will be applied later in a later release. And this is how we are calculating the capacity. Let's see how it looks like. So this is a demo about capacity. We have a pile of 600 millimeters and it has 8 bars of T25. And these are the loads. Remember them, 250 shear in each direction and minus 250 because of the right-hand rule. Keep the load in the application of the maximum compression in the 45 degrees. So 250 moment in the y direction and 250 moment, kilonewton meters moment around the x-axis. And an axial load of 2,500 downward, because it's negative, it means downward, so it's compression on the pile. And that's how the capacity ratio will look like. That maximum red one is exceeding 1. I will show you how. And these are the results. You will see the shears and the displacements are equal in both directions. Moments are equal with different signs. And the capacity ratio, the axial force is linearly decreasing because we are applying to a linear soil, so for demonstration purposes. And this beam capacity ratio it increases. Of course, there is moment at the top, so there is a value at the top. If there is no moment at the top, the value is only the axial capacity. And here the moment is checked. Then the moment is increasing and decreasing again. When the moment is increasing, see, the moment is increasing, then the capacity ratio at the maximum moment, by chance, not by chance, of course, I made this example for showing you how the capacity ratio, when exceeds 1, you will see the red cells in the table. See, the red cells are exceeding 1. So you know your section is not adequate, and you need to increase your reinforcement or change the section diameters or increase the concrete strength so that you will have a better interaction diagram. These are some references for the, let me go back. I want to show you this example in real. So the example is this one, and this is the pile, the 600 millimeter pile. And you can see there are the pile section design, the 40 MPa F sub C plat, and these are the 8 bars, 1.4%, the reinforcement ratio, distribution of the bars, I chose radial, F500 is the FY, 200,000 is MPa is the elastic modulus, the cover is 85, and everything is set here. You can understand what's happening now. Now, after the section is set, I can analyze the pile. So I press compute, and the pile is analyzed for the loads applied. The loads, you can see them here also in the edit pile. The loading, these are the loads I showed you just before a little while. And now we are ready to see the results. So after finishing the computations, you can press on graph pile. When you press on graph pile, you will get this. So this is the set of graphs, displacement X, displacement Y. These are global, not local. X prime, Y prime are local for the section. Shear values, then the bending moments, axial force, and capacity ratio. You can change these figures because we have a lot of figures that you can use. And you can also change the table. See, you can add all these to your results and take them back, and you can match the tables with the graphs. Anyway, at the end, you will see red cells for the capacity ratio that shows you have sections within the pile length that are exceeding the capacity in the factored interaction diagram. If we want to plot the interaction diagram, I go back here, then I go to interaction diagrams. I'll get this a small box. I check this circular, and I put the angle and the load. Let me see why I put specific angle and specific load. It's for convenience. So we have here 2,400 kilonewton is the axial load when the capacity starts to be above 1. That means the bending moments, which are 340, if you get the resultant of these moments, you will exceed the capacity in the interaction diagram. Let's see the interaction diagram. So this is the interaction diagram. And this alpha is the 45, and the P for this graph is 2,400. So let's see here, the 2,400 is here. See, this is the load. 2,400 is here for the 45 degrees. Why 45 degrees? Because the moments and the shears in both directions are equal, and the section is symmetric. So 2,400, I'll get here the capacity of the moment capacity. How much? It's around 460. If you calculate the resultant of 340 squared plus 340 squared under the square root, the total will be certainly close and a little bit higher of this value that we measured here. Of course, you can transfer all these data into Excel sheet, and you can use them as you want. If you have hundreds of files, you can plot them all in one graph. Anyway, in this one, we are showing the level of the interaction diagram at the 2,400 kilonewtons. So all alphas are here. The 45 degrees, where is the 45 degrees? It's this one. See, this is 0, and this is 0. This is x-axis, and this is y-axis, mx and my, and the 45 is here. You can see also, again, we are getting the same moment, around 400 something. Okay? And if we want the three-dimensional, I go and press the three-dimensional interaction surface, and I see them very beautifully, the unfactored and the factored, and I can rotate them in any direction I want. I can zoom them out and in. I can change their transparency. I can plot one and keep the other hidden, and so on. All these, and I'm very glad that you attended with me this this webinar, and these are some references. So the building code requirements is very important. You can have a look. The book by Rees and Van Imp is very important. Single piles and pile groups under lateral loading. And there's one old book, 1974. I don't think you will find it, but you can find at least materials similar to what we were talking about in reinforced concrete textbooks or advanced books. You can always refer to our website, rockscience.com. There are a lot of documents and theory manuals and verification manuals and explanations. You will find them in learning. And you choose RSPile because we have 18 products. So you choose learning, then RSPile, and you will get the documents you need. And there is a specific place for that documentation. That is the RSPile. Sorry, this is this is for the article that I've talked about, and this is the user guide that you will find everything here, or even this one. You can find it under this one. Okay, so thank you. I'm listening to your questions. I'll give like 3-4 minutes for questions, then the rest I will answer all in an Excel sheet, and we will send it to all attendees.